Good afternoon. I'm Mario Laudato from Intermolecular Inc, a business of Merck GeASSeTe Darmstadt, Germany. And today I'm going to present my work titled ALD Germanium Arsenic Selenium Tellurium Ovonic threshold switch for 3D stackable crosspoint memory. Going over the outline of my work, we will start from the introduction of the state of art for ALD chalcogenide and 3D crosspoint memory. Then we will go over the physical characterization of our germanium arsenic selenium tellurium ALD film. Then we will talk about the device integration and the OTS device performance. And we will talk about the modeling of our ALD OTS subthreshold conduction, going finally to the conclusions. Starting from the introduction, let me introduce Intermolecular. So Intermolecular from 2004 in the art of Silicon Valley develops workflow that physically and electrically characterize thin film and film stack for the material innovation in memory, logic, ferroelectrics, and quantum computing fields. From September 2019, we are proud to be part of Merck GeASSeTe Darmstadt, Germany. And during last year, we are pioneering ALD chalcogenides, especially for phase change memory and Ovonic threshold switch application for 3D crosspoint memory. But where is the memory industry with 3D crosspoint technology? Actually, the first product was released by Intel in 2017. It was the first product of Optane series. And just at the end of 2019, Micron announced the first product. But the semiconductor industry is spending a huge amount of resources in R&D to fill the gap between the DRAM and NAND, using the concept of storage class memory, where we have a fast latency and at the same time also high density and storage for the possibility to have combine the high speed of DRAM and the storage for the NAND. And in the next year, we will have more company probably in this market, and we will have more competition because it's a sort of the technology of the future. But why do we need ALD chalcogenides? Actually, the PVD 3D crosspoint memory, we can see here on the left, we have the word line and bit line, and in the middle we have the selective element that is typically OTS, and the memory element that is typically PCM, phase change memory. The selective element, the OTS, is very critical because it has to be very selective, so has to be high on-off ratio and has to sustain high on current in order to program the memory, in this case the PCM memory. But the problem for the PVD process is that it limits the film conformality and homogeneity on a large scale, precluding the integration of tens of decks in a 3D crosspoint architecture. Here we can see that we have just 2 decks. And why we use the ALD vertical 3D crosspoint? Because the ALD process allows for future 3D vertical integration, similarly with what we have actually for 3D NAND. And in this way, we can have higher density and reduce cost, paving the way for the expansion of 3D crosspoint market. And ALD chalcogenide OTS state of art, here we can see that actually we see that the research institute and university just develop binary or quaternary OTS with germanium selenium or germanium tellurium only. In our case, the Intermolecular developed a germanium tellurium film. We published this work in ICS Nano. And Seoul University developed also a quaternary germanium antimony selenium tellurium film. But in all these 4 cases, unfortunately, The electrical performances in terms of leakage and endurance were pretty poor and not comparable with actual standard for PVD OTS. We are proud to say that Intermolecular for the first time has developed a quaternary ALD OTS film with germanium, arsenic, selenium, and tellurium with electrical performances similar or better compared with PVD OTS reference in literature. So going over the physical characterization of our film, we started from the conformality uniformity of our film using a silicon trench structure with high aspect ratio, as we can see on the right, with the aspect ratio 10:20:1, and we filled the trench with a 10 nanometer thick germanium, arsenic, selenium, tellurium film. And by increasing the magnification, we can see that from the top to the middle and to the bottom of our trench, we were able to fill the trench with the same thickness along all the trench depth. And the composition analysis was carried out using a previously calibrated XRF, and we were able to define the stoichiometry of the film as germanium 23, arsenic 38, selenium 15, and tellurium 24. And the introduction of selenium in the composition was done just to increase the energy gap of the material in order to increase the resistivity, and the high content of arsenic was introduced to allow the higher thermal stability and prevent the crystallization of the film at higher temperature. So we started from a base that was germanium tellurium, and we added arsenic and selenium in order to improve the performance of our film, using also the reference of PVD OTS in literature. We also studied the atomic force through the atomic force microscopy. We studied the morphology of our OTS film, and we were able to calculate the roughness, especially going along the x-axis. We can see the root mean square of the roughness well below 1 nanometer, confirming the very high quality of our ALD film. So now let's see the device integration and OTS device performance. We started with the pre-clean of the substrate, our internal test vehicle substrate. Then we deposited ALD film and the PVD top electrode stack containing carbon buffer layer, dinitride, and tungsten. And then we went through the photolithography patterning of the top electrode and hatching and photoresist stripping. This is very common steps of IC process for the device integration. And we can see that our test vehicle allows for different device size area. We can range from 200 nanometer to 1 micrometer plug size. And studying the OTS device performance, we started from the leakage. So we measured the leakage at 1 volt, and as we can see, we were able to clearly see the device scaling on 80 device with different plug area, and normalizing the area, we were able to see that the current density was constant using different device. So it is something that suggests that, as we expect, our material demonstrates bulk conduction before forming. Going over the DC-IV characteristic, we were able to demonstrate good switching in DC regime at 100 microamps, and we were able to perform 3 DC-IV cycles, and we were able to see good switching. As we can see, the first cycle, commonly known for the forming cycle, show higher threshold voltage, and then we can see that the second and the third cycle shows pretty repeatable threshold voltage and holding voltage, that is the voltage where the device sees the switching off. And so we can see that we are able to have very repeatable subthreshold conduction and switching. Our device is really stable under long field stress during the DC operation. And using the typical half voltage scheme of a crosspoint memory, we can estimate the selectivity using the reading voltage as 2.1 volt and the half voltage as 1.05 volt. And we were able to calculate the selectivity as at least almost 10 to 4 order of magnitude of current Guidon. That is pretty good achievement. And in order to study the switching time and the threshold voltage and the holding voltage detection in pulse regime, we firstly started from applying a trapezoidal pulse with a pulse width equal to 100 nanosecond, rise and fall time equal to 10 nanosecond, and we were able to see very fast switching, faster than 10 nanosecond. It is really good for our application. And applying triangular pulse, we were able to see that the threshold voltage was around 2.1 volt, and the holding voltage was around 1.4 volt, and we were able to see clearly the switching off of our device. The threshold drift is very, very common for chalcogenide glasses, because the chalcogenide glasses tend to change electrical property over time due to the structural relaxation. And we have seen that also for OTS in literature, we have seen that it is something very common. So we studied the threshold drift also for our device. And as we can see in the inset, we apply 2 subsequent pulses with different time delay for different pulses. And every time we measure the threshold voltage for the second pulse after different time delay. And we apply 10 times this type of algorithm to measure the threshold voltage, and we extracted the median value for each delay time. And we were able to extract the threshold voltage and also to create a simple model to reproduce the data. And we were able to demonstrate the threshold drift lower than 40 millivolt per decade. It is pretty good result also compared with PVD OTS result shown in literature. In order to verify the potential use of the device in a 1s1r structure with PCM, we measured the threshold after different fall time. So we carried out this experiment using again two pulses, this time with the fixed delay time in order to avoid threshold variability due to the drift component. And we use different fall time for the first pulse, just to try to reproduce the programming condition of the PCM memories, where in the set state, in order to crystallize the film, we apply a slower quenching time. So we applied these 2 different algorithms, and we measured the threshold voltage for the second pulse in the 2 cases. And we were able to see for 20 devices that the threshold voltage between the first case and the second case showed a delta below 0.1 volt for all the 20 devices. And this is a good sign because it suggests that our OTS film is not prone to crystallization, no? And we have this result probably to the high content of arsenic in our film. Going over the cycling endurance that we carried out in order to verify the robustness of our film, we can see the pulse IV experiment. We we can see that the threshold voltage during the endurance experiment was pretty stable and just was a little bit slightly lower just after 10 to 8 cycle. We were able also to measure the subthreshold conduction using longer pulses of 10 microsecond pulse width with a higher gain of preamplifier to detect lower currents. And we were able to see that it was pretty stable during the endurance. We were able also to measure the selectivity, calculating the off current at half threshold and the ion of our device, and we were able to see stable selectivity higher than 3 order of magnitude for at least 10 to 9 cycle. Going over the modeling of our ALD-OTS film, we carried out a IV characteristic at different temperature, as we can see on the left, and we use 4 different temperature, and we were able to model the subthreshold conduction adopting the Poole-Frankel conduction mechanism. We used previous model presented in literature, and we were able also to show that we can clearly see that we have a barrier lowering, Poole-Frankel barrier lowering, where the activation energy for subthreshold conduction depend on the square root of the voltage applied. And the parameters that we use are pretty in agreement with the parameter used in literature for chalcogenide glasses. And this is something that confirms the robustness of our model. In order to also clarify the robustness of our DCIV model for subthreshold conduction, we characterize also the modeling for full IV, and we were able to see that calculated IV with our model was in good agreement with the experimental data, and the model could be used for future development of ALD-OTS device through the fine-tuning of the film thickness and composition. Going over the conclusion, we can say that we integrated for the first time an ALD quaternary OTS with germanium, arsenic, selenium, tellurium, and we demonstrated high selectivity, excellent endurance, low threshold drift, and very fast switching. And we successfully proposed a model for germanium, arsenic, selenium, tellurium OTS subthreshold conduction. And this is something that paved the way for the future development of ALD chalcogenide film for selector use in 3D crosspoint memory arrays. So thanks for your attention, and see you on the conference platform.